Hello, grade 10s. We're going to join Eloise again as she looks at patterns in bus timetables, the height a ball bounces, and the exponential pattern that forms the concept behind the movie Pay It Forward. Let's see what she's doing.
Have a look at the people at this bus stop. Do you see any patterns in what they are doing? Do you see the vendor over here? When a bus arrives, she is always ready to sell her fruit. Yet soon after the bus leaves, she takes her fruit and leaves as well. She seems to know just when to expect the bus. I wondered how she knows what to expect, so I asked her. Her name is Thandi. Listen to what she had to say.
When I started, I sat here the whole day. But I think I was just wasting my time. Yeah? I thought I should be selling somewhere else. But my friend gave me a good idea. She said I should see what times the buses stopped here over a few days. Then work out a pattern in the bus time and use it to decide when was the best time for me to sell my fruits here. Hey, Ash! This wasn't so easy. I got up here at half past 5 and packed everything because the first bus was coming at 6:10. There was another one at 7:20. The next one came at 7:15. Hey, I was starting to think that I couldn't see any patterns because the next one came at 5:08. I wrote down the 4 times the buses stopped. 6:10, 7:20, and the next one came at 7:15. Then I saw it. There were 30 minutes between these times. 35 minutes here and 40 minutes between these 2 times. I started getting bored with waiting around, and so I tried to predict when the next bus will come. I could see that the times between buses stopping always increased with 5 minutes. So I reckoned that the next bus would arrive 45 minutes later at 9:20. And it did too. Give or take a few seconds. Then by adding 5 minutes to the amount in between buses stopping, I carried on until I got to 12:30.
That was quite a clever idea that Thandi's friend had. Let's see if we can work out the bus times for ourselves using Thandi's pattern. If we use her rule that we must add 5 minutes to the time between buses, we can write this as a number sequence like this. Now let's continue the pattern. We need to add 50 minutes to 8:40. That's from 20 to 9 to 30 minutes past 9. 55 minutes after that is just 5 minutes less than 1 hour, so it's 10:25. Then an hour from there is 11:25. Then it will be 12:30. Let's do 2 more. We add 70 minutes to this to get 13 hours 40 and then 14:55. I wonder if these are the times that the buses actually came. Let's ask Thandi.
Well, no. Something went wrong here. The bus that was supposed to come at 9:30 came 10 minutes late. I didn't a mistake. The next one came at 10:40 instead of 10:25. The other one came at 11:40 instead of 11:25.
Let's write these bus times underneath the pattern we predicted. Can you see what has happened here? Let me show you. Look here. There has been an hour between these 2 buses arriving and another hour between these 2. Using the new pattern, the next bus should be at, let's see, an hour after 11:40 is 12:40. Thandi also told me that she watches the buses for a few days and recorded all the times that they stopped. She found that the pattern changed again later in the day. This makes sense because more buses are needed at the beginning of the day when people are going to work and at the end of the day when they are going home. Once Tandy knew the patterns, she found that her predictions about times became pretty accurate. What she also did was to estimate how many people got off the bus at a particular time. She noticed that when the bus times were closer together in the morning and the evening, there were more people using them as well. So she decided to sell her fruit at the bus stop over the busiest times and to move to the nearby school in the middle of the day. Well, that's not all I noticed at the bus stop. Have a look at the scene again. Do you see the boy bouncing the ball? That is Josh. He's always trying something new. What do you think he's up to? He could be counting the bounces, but he isn't throwing the ball. He's dropping it from different heights. It looks like each time he drops the ball, his friend Pete tries to count the number of times the ball bounces back and drops again. Almost like he's doing some kind of experiment. Perhaps he is set to be a scientist when he grows up. Let's take his pattern and look at it more closely. We want to see what height the ball bounces back to each time. First, he drops the ball from a height of 0.8 meters. Look at this. He drops the ball and it bounces back up to a height of 0.4 meters from the ground. That is exactly half the height it was dropped from. Do you want to make any guesses about the height of the next bounce? The ball drops back down to the ground and bounces back up to reach a height of 0.2 meters. That is half the height of the first bounce. Do you think this will happen again in the next bounce? Josh and Pete checked this for a while. Josh managed to get the ball to bounce back 7 times. He couldn't measure the height of each bounce, but it looked like it was half of the previous bounce each time. Well, more or less. Let's study the pattern here, even though Josh's ball doesn't always bounce the way we want it to. Real patterns are like that. Your measurements won't always be accurate. Every now and then, the ball might hit a stone, or Josh might not drop it straight down, or he might even throw it instead of just dropping it. So if our measurements were always accurate, how high will the third bounce be? The third time the ball bounces back, it reaches a height of 0.1 meters. Suppose the ball still bounces back another 5 times before it starts to roll. Can you predict the height of each of the next 5 bounces? It will help to set this up in a table. We are comparing the number of bounces with their heights. So the first bounce was 0.4 meters high, the second bounce was 0.2 meters high, and the third one was 0.1 meters high. Can you see what pattern is being created here? Each bounce is half the height of the previous bounce. Do you think you can use this pattern to work out the height of the 4th and 5th bounces? If you worked it out, you would get 0.05 for the 4th bounce and 0.025 for the 5th bounce. Half of 0.1 is equal to 0.05. Remember that you can write 0.1 as 0.10, and half of that is 0.05. Don't get this mixed up with 0.5 or 0.50, which is much bigger than 0.1. This gives me the height of the 4th bounce. For the 5th bounce, we halve 0.05 to get 0.025 meters. The height of the 6th bounce will be half of 0.025 to get 0.0125. The height of the last bounce can then be found by halving 0.0125, which gives me 0.00625. I will leave you to check that my calculations are right. But how much is 0.00625 of a meter? Well, let's convert that number to centimeters and see. There are 100 centimeters in a meter, so we can multiply by 100 to get 0.625 centimeters. Gee, even that number is small. Let's try writing it in millimeters. There are 10 millimeters in a centimeter, so we get 0.625 times 10, which is 6.25 millimeters. That's this much. Can you imagine getting a ball to bounce exactly this high? I'll have to see it to believe it. And just think how small the next heights will be if it were possible to bounce the ball so that it never stops. Mathematically, this pattern works. It could continue in the same way to infinity. We could keep halving these small measurements and, well, we could never get to zero. But actually, the bouncing ball starts rolling after a while and then it stops. The height that the ball bounced was getting really small and difficult to see. The numbers we used to describe this were getting closer to zero without reaching zero. Now I would like to show you a pattern where the numbers become very large. You might have heard about the movie Pay It Forward. For those who didn't, a young boy chooses a project for his social studies class. This is what he proposes.
If someone did you a favor, something you couldn't do on your own, and the next day, instead of paying it back, you paid forward to 3 other people, and the following day, they paid it forward to another 3 people. In 2 weeks, that's 4,782,969 people.
That's quite a big number of people starting out with 3 little favors. In the film, he starts the process by doing favors to 3 people and requests that they pay it forward to 3 people. Will this really reach close to 5 million people in just 2 weeks? Let's check that the numbers work. I think the best way to start would be to put the information onto a diagram. If you are the person starting the favors on the first day, then 3 people will receive favors. On the second day, each one of the 3 people will then pay it forward to 3 other people, and therefore 9 people will receive favors. On the third day, each of the 9 people will then pay it forward to 3 other people. That's 9 here, 9 here, and 9 here. 27 people in just 3 days. And on the 4th day, these 27 people will each pay it forward to 3 people. Can you work out how many people that is? You could count up in 3s again, but I hope that you saw the pattern. We can simply multiply 27 by 3, which is 81. That's 81 people who would receive favors. What about the number of people that receive favors on day 4? We can take 81 and multiply by 3, 243 people who would receive favors. If we kept going until we reached day 14, we would have to do a lot of calculating, and there would be a chance that we might get it wrong. Or do you see a pattern that will give us a shortcut here? So far, we have the number sequence 3, 9, 27, 81, 243. We could write 9 as 3 squared, 27 is 3 cubed, which is 3 times 3 times 3. 81 is 3 times 3 times 3 times 3, which is 3 to the power of 4. And I could write the first 3 here as 3 to the power of 1. Let's use a calculator to see what we get for 3 to the power of 5. 3 to the power of 5 gives 243. It looks like the pattern is 3 to the power of something. Here, on day 1, the power is 1. On day 2, it has a power of 2. Day 3, 4, and 5 work like that as well. So the number of favors done on day 6 will be 3 to the power of 6. Let's work that out. Using a scientific calculator, we press 3, then x to the power y, 6, and then equal to get 729. So we can use our pattern now to get the answer for 14 days without doing lots of multiplying and adding. For 14 days, the number of favors will be 3 to the power of 14. That is, press 3, then x to the power y, 14, and then equals, the answer is 4,782,969. Great! That's the number that they used in the movie. It only took 14 days for nearly 5 million people to receive a favor from someone else and to pass on 3 favors. Isn't it amazing that one person could influence so many lives in just 2 weeks?
Thank you for joining us, grade 10s. Remember to look at the tasks for this section in the Numbers and Patterns tasks video. You'll also be able to learn more on our website, www.mindset.co.za/learn.